Let's talk about using the standard normal distribution table, which is also known as the Z-table. Hi guys, hope you're doing really well. Okay, we're going to talk about the standard normal distribution table. Now, the standard normal distribution table is another way to deal with the normal distribution. Remember, we have, if you've been watching these videos, we've been using in the past, we used the empirical rule. As a matter of fact, you can, let me spell it out. You can review probability distributions for continuous random variables, part 2, my video by that name, where we talk about the normal distribution and using the empirical rule to divide it up into proportions. For example, we can go from -1 standard deviations to +1 standard deviations. That means a standard deviation below the mean of a distribution to 1 standard deviation above the mean of the distribution. And the empirical rule gives us a pretty good figure for the proportion that would be found in that zone. As well as within other zones, we can go from -3 to +3 standard deviations with the empirical rule. And it's an estimation, it's an approximation, but it works pretty well. The only problem with it is that it only works for these integer values of standard deviations above and below the mean. So from -3 standard deviations to +3 standard deviations. So really it would be useful if we had something much more accurate, and we do. So we're going to take a look at that. That's going to be the standard normal distribution table. So we're going to talk about the standard normal distribution table, and it's a much more powerful and much more flexible way of talking about proportions of the normal distribution. But to do so effectively, we should get some vocabulary out there. Now, this is going to be review for most of us, but just in case it isn't, or just in case your memory needs a little jogging, let's talk about a Z-score. So a Z-score is the number of standard deviations above or below the mean of your score. So for example, if I have a mean of 10 for a population or a sample, and a standard deviation, let's make it 2 because it's an easy number, well, I have 1 standard deviation above the mean, which means to the right on the number line, which is basically what this is. I have a score at 12. Now that's 1 standard deviation above the mean, so therefore its Z-score would be +1. That's the idea. If I have a score that's at 15, that's now 2.5 standard deviations above the mean. So its Z-score is 2.5. Realize that that might happen and that we couldn't use the empirical rule to start talking about that score because it's not 1 or 2 or 3. There's a formula for Z-scores. Let's look at that formula and just make sure that we're all familiar with it. The Z-score that you're looking for is the number that you're examining minus the mean of the distribution divided by the standard deviation, which is basically what we just did mentally on the distribution that I just erased. There is no problem if you get more used to thinking of it in these terms, because that's actually the same formula, isn't it? That's just using symbols that represent a sample, whereas this is using symbols that represent a population. But conceptually, it's the same thing. So for example, let's take a distribution with a mean of 70 and a standard deviation of 12. By the way, you should be able to tell immediately that I'm talking about a population because I've written mu and sigma for the mean and the standard deviation. That's Greek letter mu and Greek letter sigma to indicate those things. Now we're given a score of 91. What is that Z-score? Let's figure it out. I'm going to erase the formula and plug it in with those numbers. Now with the Z-score formula, and there's a couple of different forms beyond the ones that I just wrote for different purposes. It's pretty much always a fact that The score whose z-score you are solving for goes in the upper left. And the mean of the distribution will go in the upper right. And then we're going to we're going to divide by the standard deviation. So that's actually 21 divided by 12. Well, doing that, I'm getting 1.75. So we find that we can say that the z-score of 91 is 1.75. So that is 1.75 standard deviations above in the positive direction from the mean. Hope that makes sense. Let's continue trying those. We'll do a few more examples. Let's try it again, okay? I hope you have that formula written down for z-scores, because I'm going to write out the mean of a population and the standard deviation of that population. And I'm going to ask you to solve for the z-score of 29.2. Go ahead and try that. Pause the video, and then we'll do it together. Let's see what score you get. Okay, well, let's go ahead and solve for that. If you decided to do it on your own, you probably hit play again by now. So I'm going to plug in these numbers again into that z-score formula. So we have the score that we're solving for. Let me do this properly. The score that we're solving for in the upper left, the mean on the upper right, and the standard deviation below, dividing that difference. And I got 2.25 z. So I hope you got the same thing. I want you to notice something. I'm putting the score, again, I can't make this, I can't overstress this. The score whose z-score I'm solving for is in the upper left. There will be times when you solve for a z-score that's negative, and people have this instinct to subtract a small number from a big number, and that's not always the right thing to do, and it'll end up giving you the wrong sign of z-score. I'll show you an example of that happening next. Here's another example that shows us how important it is to make sure that we're using the formula right. Imagine that we have the same situation as we had just a moment ago, where we have a distribution with a mean of 22 and a standard deviation of 3.2, and then you're asked to find the z-score of 16.24. It is really a temptation to subtract 22 minus 16.24 and put that on the top of the fraction where we solve for the z-score, and then divide by the standard deviation. The only problem with that is we would get the wrong answer. Even if it seems like you're going to come out with a negative number, you put the number that you're examining, the x, the score, whose z-score you're solving for, you put that on the upper left. Because when you do that, you're going to get a negative number at the appropriate time. So if you do this problem, as a matter of fact, go ahead and pause the video for a second, solve for it, and we'll see if we get the same thing. Okay, I'm going to go ahead and put down the answer that I got, negative 1.8. It's supposed to be negative in this case. We're solving for the z-score of a score that's less than the mean. If we were to draw a picture of that, it would look like this. We have a normal distribution. Actually, just in terms of z-scores, it might have been any distribution. But let's stick to this idea that we're working with normal distributions today. So we have a mean of 22, and we're checking for the z-score of 16.24. Now that's to the left of the mean. It's supposed to be negative. The z-score of the mean itself, if you were to plug it in, you'll find that it's 0. And scores higher than the mean are positive, and scores lower than the mean are supposed to be negative. So even though 16.24 is a positive number, the z-score of that is negative because it's to the left of or less than the mean. Okay, I hope that makes sense. Next, we're going to take a look at the Z-table. You're going to find this online or in any statistics textbook, and we're going to take a look at how to read it. So that's coming up next. Okay, so we have reviewed Z-scores, which are going to be important for us. That's really necessary for us to do what we're going to do, which is to explore using the standard normal distribution table. But let's keep an eye on the ball and figure out and make sure we're aware of what it is that we are doing right now. You have, let's just suppose, some phenomenon that you're examining where the phenomenon is normally distributed. And as a normal distribution, it's going to be symmetrical, and it's going to have a mean right in the center and some standard deviation. And just like the empirical rule, we can divide this distribution up and talk about areas, let's say, to the left of some landmark or another. I'm going to mark this line Z star because in the language of standard normal distributions or normal distributions in general, Z star is a way often of talking about the score that you happen to be working with at that moment. So we might have any mean, any standard deviation, and any score that we're examining for the moment, but if we translated that score into a Z-score and then utilized that Z-score in looking at the standard normal distribution table in a way that I'm about to, we're going to do that together, and I'm going to explain how in a couple of moments. Then that standard normal distribution table, that distribution table, that Z-table, and it's called all these things, will very often give us the area from the left up to the point that we're examining. Now, is that the only way that they work? No. As I said, there are variations. There are Z-tables, normal distribution tables, that give you area only from the mean to the score that you're examining. That's not that unusual. There are standard normal distribution tables that give you the area around some symmetrical zone. Remember, we're not talking about the empirical rule anymore. So these can be mirror image, non-integer values of Z. That is possible. If you want me to explore this more or you have questions about this part, let me know in the comments and I'm going to answer you. So my point for the moment is there are different formats of normal distribution table. That's really all I mean. However, the one we're going to be working with is a very common type, maybe the most common type. And the way that ours is going to work is that we're going to look up on a table, given that we've solved for some Z-score of some score that we have, it's going to give us the area to the left of that, and then we can utilize that in any number of very clever ways. Okay, so how are we going to do this? Well, I'm going to be giving you stills. I'm going to flash some stills on the screen, and it's going to be there for, let's say, about 7 seconds, and it's going to give you a chance to look at it and check your work versus what we're doing. So I'm expecting that a lot of you guys will have your textbook, a stat textbook or something, in your lap, and you can look up in your tables exactly what we're doing on screen. So when you see these stills, go ahead and pause the video and make sure you can find the same thing in whatever resource you're using. I've made my own because I wanted it to look a certain way, and also because of copyright issues and other issues that I didn't want to deal with, okay? So let's start this way. I'm going to go back to one of the examples that I had early in this video. Let's imagine that we have a distribution with a mean of 70 and a standard deviation of 12. And I think I said, let's talk about a score of 91, right? And we solved for the Z-score, if I remember right, it was 1.75 in this case. So the Z-score of 91 is 1.75 according to this mean and this standard deviation. So what we're going to do in this part of the exercise is we're going to take a look at the area in a normal distribution that would be to the left of z equals 1.75. And that's what we're going to solve for first in this part of the video. So go ahead and get your z-table, and we're going to do that together. My z-table looks like this. Okay, so if you're looking at a table in a book, it's going to look a little bit different from mine. You'll notice that I made some modifications on mine. I deleted some rows, and mine starts on the left from 1.4 and goes down. But basically, it's the same as most of the tables you're going to be finding in your book. So we're going to go ahead and take a look at it. The first thing you want to do, I hope you have your table, your resource in your hand. The first thing you want to do is find the 1.7 along the left-hand column, okay? That's going to look like this. Okay, now that you've found that 1.7 on the left, I want you to go up to the top of the table and look at those decimals. They start from 0.00 and go across to the right to 0.09. That's actually supposed to be the second decimal place. Now remember, we started out by looking for 1.7 on the left. That you can think of that as 1.70. That's on the left. That gave us a row. We really want 1.75 though, so we want a 5 in the second decimal place. So what I want you to do is read across the top until you find 0.05, and then read downward and take a look where the 0.05 column intersects with the 1.7 row. You're going to look for that intersection point. That's going to look like this. Okay, I hope you're following along, and I hope you found that same value on your table that I found on the table that I just showed you. We looked up the area on the table for z equals 1.75, and if we're getting the same answer, you got 0.9599. Wait a second. What does that mean? Well, it means this. For any normal distribution, the area to the left of 1.75z is going to be 0.9599 of the whole. Another way to say it is 95.99% of the whole is to be found to the left of that score. Okay, if that isn't true, it's not a normal distribution. I should probably be a little specific about another point too. Is this an exact figure? This is clearly more precise and more flexible than the empirical rule, but is this thing going to give us an exact value? No, even that is an estimation. If we solve for the exact area, and it's a little complex to do that, you can't use normal integration techniques in calculus, which is what a person might expect to use. You're going to find that the decimals go on forever. So even that is an approximation, but it's so close that we often treat it as if it's, well, maybe I can't say it's exactly correct, but it's as precise as we would need to be in very, very many situations. So I hope you got the same score that I did and the same area. And let's go ahead and do another exercise. Okay, guys, here's another example from the beginning of this video. I think I proposed, hey, what about a distribution that has a mean of 22 and a standard deviation of 3.2? And we're solving for the score 29.2. And we found that that score had a z-score of, I'm looking at my notes, 2.25. So let's go ahead and look at that on the table and see what the cumulative area is. Remember, that means the area that would be found to the left of z equals 2.25. I hope this is making sense to you. Comment with questions, let me know. So let's go to the table. The first thing we're going to do is find the row that says z equals 2.2, right? That's going to be the ones number and the first decimal value. That's going to be in the column to the left. It's going to look like this. Next, we're going to find that 5 column again, just like we did before, and we're going to find where they intersect and read the area there, and that's going to look like this. So the area I'm finding to the left of that point is 0.9878. So that's the area to the left of z equals 2.25. That's 98.78% found to the left of that. By the way, this allows us to gain a little bit more insight about the normal distribution. So all we need to do is to go 2 1/4 standard deviations to the right of the mean, and we've already got behind us to the left almost 99% of the whole distribution. So when you hear somebody say that z equals 3.5 or z equals 4.0, those values that are very high, when you hear someone say that those are functionally infinity, what they mean is that you are so far beyond the vast bulk of the normal distribution that, you might as well just be all the way to the horizon. You've got almost 100% to the left of z equals 4.0. As a matter of fact, it is so close to 100% that we would commonly just round that to 100%. And even z equals 3.5 very often gets rounded to 100% in terms of the area to the left of it. Okay, so let's continue. Okay, just for fun, I looked up what's the cumulative area to the left of z equals 3.5. And as it happens, on the table that I use very frequently, it came out to 99.98. 99.98% is found to the left of 3.5. And if you go any higher than that, you just have a longer string of nines until any decimal point you want. The table that I use actually rounds z equals 3.89, it rounds it to 1.000. So that just gives you an example of how quickly this thing sort of peters out. By the time you're just below 4 standard deviations to the right of the mean, then you're going to find that the area is virtually 1.0. If we went to more decimal places than that, if you're using software, for example, which is what you're going to use if you're going to end up being a working statistician, then you can specify that it would give you 10 decimals, for example, and in that case, you'd have a very long string of nines before a non-9 numeral. But it would still, for most purposes, round to 1.0. Something else I want to point out, please. If we have a z that's in the negative, z equals negative 2.0, the value that you're going to find is going to be much less than the majority. For example, if you have z equals 0.00, look it up on the table, you'll find it's the mean, and it's going to give you a cumulative area of 0.500. That should make sense to you because the normal distribution is symmetrical. So when you're right in the center at the mean, which is z equals 0, you should have exactly half of it to the left. What is the area that you're going to find to the left of a negative value? Well, it's going to be much less than 0.5. In the case of negative 2, it's 0.0228. Okay, so far less than half. In fact, just over 2.25%. That's the area you're going to find in what's called the tail. So I'll draw a smaller picture this time. Z equals negative 2. Here's the tail. Obviously, my drawing doesn't have exactly the right proportions, but this gives us an idea. So the area to the left of z equals negative 2 is very small, 2.28%. let's compare the empirical rule versus the standard normal distribution table, which I'm also going to call the ZTable. And this will be a good exercise for us. Remember what the empirical rule tells us, that, let me draw a picture, that the area that you'll find between z equals positive 2 and z equals negative 2, that area is going to be 95%. And that's not necessarily the case. The empirical rule is an approximation, a very good one, but the Z-table is a better approximation. So what I want to do is I'm going to instruct you on how to do this. Then you're going to pause the video and we're going to make sure our answers match. What does the Z-table tell us about the area between these 2 points? The way that you're going to have to do this is first to look up the area to the left of z equals 2.0. You're going to get a value, right? That's going to be some value. That includes the area that we want from z equals positive 2 to z equals negative 2. It includes that whole area plus the tail, which we do not want. So I'm going to have you look again on the Z-table. I just gave you the value a few moments ago, but you know what? Go ahead and find it yourself. Find the area to the left of z equals negative 2. And you're going to subtract this area from this whole area, and that way you'll be left with just the area in between, and that's going to be the answer. You know how to read the Z-table now, so go ahead and do that. Okay, so we're looking at the proportion of the Z-table, and you can think of this as probability also, between negative 2 and positive 2.0. And if you looked it up on the table, you found that the area to the left of positive 2 was 0.9772. So that's the hole that we're working with. We want to lop off this tail that is located at z equals negative 2. We want to cut that off to be left with just the value in between. So we're going to take this greater value, not 0.9772, and figure out the area in that tail to the left. My drawings are getting sloppier and sloppier. And find out what's in between. Now this area was 0.0228. When you subtract 0.9772 minus 0.0228, you're going to get 0.9544. And so we see a couple of things. That the empirical rule value of 95% to be found exactly between those 2 points is a pretty good approximation. We also notice that it's not exactly right. And you're going to find, and this is a number that if you study statistics for any length of time, probability and so on, this is a number that's going to end up being burned into your memory. According to the Z-table, you need the value of the area between positive and negative 1.96z to get 95%. At some point, I'm not going to ask you to pause the video for this one, but at some point, go ahead and look that up on your own. I want you to see that that's the case, okay? As a matter of fact, maybe I'll show you a picture of a table and where to find that. Okay, so you should be able to find the equivalent point on your table. There are a lot of values that get used repetitively in statistics. There's a few values, like for example the value that gives you exactly 90% in between, where we fudge a little. I want you to take a look at the value on your Z-table where if you take it and its twin on the left, you'd have exactly 90% in the middle. And I'm going to ask you to take it on faith at this point that that's going to be repetitively useful, okay? Just as it happens, just believe it for now. I can't in this video explain exactly why, but it's going to be a very useful video. Now what that means is that you're going to be looking up a value where there's two values. Let's call them Z star and negative Z star, where in between you have 90%. Remember that the whole of this thing is 100%. And that means that if we have 90% in the center, we have 10% total in the two tails. If we have 10% in the two tails, then that means that we're going to have 5% in each of the tails individually. If you need to, stop the video, rewind it, and get that part again, because that's a bit of thinking that we're going to reuse time and time again. So what we want to find is the Z star and negative Z star such that that is the case. Well, okay. The nice thing is we only have to look up one value. How come? Well, we can see that whatever Z star is, it has 90 plus 5% to its left. So all you got to do is go to your table and look up the value that has 90 plus 5 or 95% to its left. Go ahead and take a look at it, and I'm going to pause and give you a second. You're going to pause the video rather and take a look at it. Okay, here's the issue. You went to your table and you found something that was kind of ambiguous. You hopefully found that on the 1.6 row, there were two values, 0.04 and 0.05, that seemed to be about equally distant from that value of 0.95. Okay, how do we deal with this? Well, what most people will do is, like for example, instructors in a stat course will say, use this one or use that one. What I like to do is to actually split the difference. I take the mean of the two values. So for me, the best value to find for Z star such that the area between Z star and negative Z star would be 90% would be 1.645. I feel like I didn't put that entirely clearly, so let me say that again. Z equals 1.645 and Z equals negative 1.645 gives me very close to 90% between. Even that isn't entirely accurate, but it's certainly good enough for most of the work that we're ever going to do in the natural sciences, medicine, and demographics, and politics, and so on. That's pretty much the value that they use when they're not looking it up in software or in a software package. Okay, let me lay out some questions for you to work, and we'll see how you do with those. Okay, so here's some problems I want you to work, and I'm going to do a follow-up video to give you the answers to these. Here's 3 problems, and in no way do I think that for the average person 3 problems is really enough to master this. So you want to go out and seek more problems than just this. This is a taster. It's an intro of various types of problems, and you want to definitely do more to become good at this, and that's going to be necessary for any stats student. Here's the problem. So for the first one, let's propose a distribution with a mean of 10 and a standard deviation of 1.8, and I want you to give me the proportion of that distribution that would be found between 10 and 13.3. It's not a bad thing to keep in mind that you could equally read this way. What is the probability of a randomly selected value from this population having a score between 10 and 13.3? It's really the same question, isn't it? As long as the distribution is normally distributed, we can phrase the question either way. Here's the second one. We have a population with a mean of 122 and a standard deviation of 14. What is the probability of a randomly selected score from that population having a value between 100 and 118? Okay? Or what's the proportion of that distribution? Same thing. Now remember, with both of these problems, you're going to need to first translate the values you're working with into z-scores, and then use those z-scores on the table to get the area, okay? Here's the third one. From a population with a mean of 40 and a standard deviation of 6, I want to know the proportion of that population, of that distribution, that is greater than 10 units from mu. Now that's kind of vague. Sometimes that confuses people. What do you mean 10 units? I don't mean 10 standard deviations. That would be ridiculously huge, by the way. That'd be 60. So that's not what's meant here. I don't know what the unit of 40 is. And I don't know what the unit of 6 is. Maybe this is a mu of 40 degrees. Maybe it's a mu of 40 gallons or a mu of $40, or it could be anything that we're studying. But whatever those units are, and by the way, those have to be the same units, right? Whatever those units are, I want to know the proportion of such a distribution. And remember, all of these are normally distributed. The proportion of that distribution that's going to be more than 10 units away from mu, okay? A little bit more conceptual, a little bit more abstract. I think you can do it. Go ahead and try that. Comment on the video as you like at the bottom, and I'm going to follow up with some answers with a follow-up video, okay? Thanks a lot, guys.